Hi. Okay. All right. So, in the last lecture, we talked about the definition of voltage, and we talked about the definition of current. Okay? Voltage, units, are volts. A volt is equal to the amount of joules, which is energy, and the amount of coulombs, which is the number of electrons. Okay? Current, amperes, that is the unit of current, which is equal to the number of coulombs per the number of seconds. So if you have 1 coulomb of electrons traveling per second, you have 1 ampere. It's much like saying I'm dumping 1 gallon of water down the drain at a time. Similarly, volts is the amount of energy per coulomb of electrons. It's like saying I have 365 potential energy per human standing on top of a bridge. None of that made sense. But that's voltage and current, okay? In this lecture, we're going to be talking about power. See, power is one of my favorite topics because power is everything. It really is. I'm wearing my Infinity Instructor Gauntlet. See, I always want to understand power. Why? Because it's really kind of fundamental to this class. Power is really fundamental to everything in physics. Everything is about power. Where is energy going? Now, the base definition of power, the unit is a watt. It's not a question. Also, hi, Dylan. Hi. I like how so far you've said 2 words and both of them started with H and both of them were 2 letters long. It's awesome. Okay, the base unit for power is a watt. A watt is equal to a joule per second. Okay, a joule is base energy for, well, it's base unit for energy. So this is the amount of energy change per time. And that's what power is. It's energy change. Energy takes many forms, which is why power is so useful. Because energy could be light energy, could be heat energy, could be electric energy, which is the voltage multiplied by the number of electrons. Okay, it can be a number of different things. It could be speed energy, how fast an object is traveling. Power is really, that right off the top of the screen. Ah, dang it, Kale. Oh, and by the way, I'm wearing pants. You probably couldn't see that earlier. I like to wear pants when I give lectures. Okay. So, power is really what combines everything. When you look at a Tesla, okay, if we're just going to jump into the example of a Tesla, okay, Tesla has a lot of energy stored in batteries. It's electric energy. It's electric. Okay, it's got energy stored in batteries. Now, the amount of energy that is drawn from those batteries per time is power. So, how much power is being drawn out of those batteries then goes into an electric motor. In this electric motor, electrical power is converted into rotational power. It uses a bunch of different coils and copper components, a lot of copper. Sometimes it'll use carbon nanotubes, sometimes it'll use platinum. It really depends on the how good the motor is. But in any case, using coils and apertures and everything, that electric power is converted into rotational power. That rotational power then goes into a gear train, where that rotational power is converted into, well, I guess that's more the transmission than the gear train. Gear train, it converts rotational power into rotational power. Transmission converts rotational power into translational power, and what you have is vehicle speed. Okay, this is how power works. Power exists in this form, exists in this form, exists in this form. Power is everywhere. It's through all of these. It starts as electric, it ends as vehicle speed. It's actual physical translation. This is why power is so important. It is what unifies the entire physical known universe. Power is everything. And we talk a lot about power in this class because power is everything. Power is needed to understand how electrical systems work. We need to know friggin' power. And power calculations, if you get into the mentality of calculating power, everything starts making a lot more sense. What is the power that's going out of that resistor? Where is that power coming from? Every bit of power has to come from something. There's power that has to go in to charge this battery. Okay, you're using a charging station. That means that power is coming from a charging station. That power going to the charging station is coming from a power transformer. That power transformer is getting its power from a power plant. Okay, where's the power plant getting its power from? Well, power plant, oftentimes they run off of steam cycles. What a steam cycle is basically you heat up some volume of water some way. Maybe that's burning coal, maybe that's using nuclear material. But you heat up this water, water expands substantially as it turns into steam. That expansion is plugged into a system where it goes through a turbine, causes a turbine to spin. That spinning turbine, ironically, works a lot like an electric motor in reverse. It causes something to spin that generates a certain amount of electrical power that comes out of it. That electrical power then jumps into the power grid. Okay, so this power plant is getting its energy from coal, solar, something. I mean, it's just how power transfers. How is this power being consumed? How is it changing form? Here, if it's coal, it's chemical energy. If it's solar, if this was a solar array, then it's coming in as electromagnetic energy being transformed into an electric voltage difference. Okay, power has to come from somewhere, go somewhere else. Where does power ultimately come from? Well, that will depend on your theology. If you believe that everything came from nothing, there is no answer to this question at all. I'm a religious person myself. I believe that all power eventually had to have been created by an exterior force. So whatever you believe, power has to come from somewhere, go somewhere else. We have never observed power suddenly spontaneously being created. It has to exist in some form, come from somewhere, go to somewhere. And monitoring that power transfer, power tends to be conserved. We can figure out where all the power is going. Now, at each stage of this, there's going to be some heat loss. And there's going to be some amount of heat generated per time. Heat per time, that's power. Okay? And you're going to be losing some of that power to heat at every one of these stages. Okay? And quite frankly, the vehicle speed, it goes into heat. You're moving air, large bodies of air as you travel through that air. All of that air forms viscous resistance, which turns into heat as well. The fact that we move creates heat. But you can monitor where all of that power is going. And if you understand the heat losses, you can still monitor where all that power is going. Everything is about power transfer. Power transfer. Why is everything about power transfer? Because power is the most fundamental unifying aspect of physics. Okay? And it is most important when you're a mechanical engineer because you deal with a lot of power, or an electrical engineer because, again, you deal with a lot of power. The calculations are a lot cleaner for the electrical engineers. Power is critical. It is. You plug too much power through a component, your component's going to explode. Okay? By the way, 1.21 gigawatts, a gigawatt is energy. That's not power. It should have been, wait, no, I'm wrong. 1.21 gigawatts is totally power. That's not, I'm trying to show how hip and cool I am by referencing Back to the Future and just showing that I'm an absolute nerd and can't speak. Whatever. Well, call me mom for reassurance and validation. Okay. So, power is the fundamental unit. What is power in an electrical circuit? Okay? Power is given by, it is always, and here the clicker is, this is always true. For an electrical circuit, power is equal to voltage times current. Okay? Voltage being your joules per coulomb, current being your coulombs per second. This is when these multiply, it becomes a joule per second. Okay? This is why this is always true. It does not matter the component. It doesn't matter if this is an LED. It doesn't matter if this is a resistor. It doesn't matter what this is. This always remains true. Power equals voltage times current. Okay? This is one of the foundational equations for this course. This is one of the foundational equations for this course. You need to know this equation. Write this on every single paper you own. Okay, I don't care if it's money. Write this on that. All right? Foundational for this course. You need to know this. I'm not going to make you memorize it because you can write down formula sheets as much as you want. But you will use this so much you probably will memorize this. And it's not a bad idea to memorize this. Okay? Power is equal to voltage times current. All right, so let's move on and talk about energy, okay? Because energy, if we're going to talk about power, we need to talk about energy too. What is energy? Well, I've heard some people say that energy is the ability to do work. Some people say energy is, well, it's the integral of power. Energy and power are fundamentally linked. Because both of them exist in a time scale. The energy change per time, the other definition of power, power is equal to the derivative with respect to time of energy. Okay, you can flip this around and you can say energy is equal to the integral of power with respect to time. Okay, both of these are valid and both of these are true. And they are true indefinitely in every system. Doesn't matter if we're talking about a mechanical system, doesn't matter if we're talking about wind load, doesn't matter if we're talking about rotational energy, or it doesn't matter if we're talking about speed, it doesn't matter what type of energy this is, the power is always going to be the derivative with respect to time. Or the energy is going to be the integral with respect to time. Okay? So, power and energy are like father and son traveling through the forest together, always together, ho ho, fighting dragons together. One of them just happens to be derived from the other with time, which I guess could be an analogy for like a child, except the child wouldn't be power unless the old man. I went too deep on that analogy. I'm fighting dragons in my head. Awesome. I need a cape. Okay, so ultimately what energy is it's the ability to do work. Okay, what is the ability to do work? Well, it's the ability to transform energy components in a system. For example, if you have a lot of energy stored in an electrical capacitor or in a battery, you have a lot of energy stored there. Really what that is that energy has the ability to be transformed into power to be used in some fashion, whether that's generating heat, generating light, generating motion. Okay? Energy is transformed between multiple different forms. Sometimes it's potential, sometimes gravitational energy, sometimes it's electric energy, sometimes it's kinetic, sometimes it's heat. There's a lot of different kinds of energy. And energy transforms between all of them. It is, with power, it is also a defining, unifying feature that exists in all of physics. Again, it's important to understand the energy because the energy, well, you can figure out, if you figure out power, you can figure out energy. Similarly, if you figure out energy, you can figure out power. Awesome. Okay, but it allows us to understand how energy is transformed and how things are changed because of the energy that is present and how we're able to draw that energy. Okay? And how we're able to use that energy. One thing that you can, if you know anything about fires, I've burned a lot of things in my life. Again, I'm throwing this out on the internet because I'm brilliant. I know a lot about fires. Well, I've burned a lot of campfires in my life. Okay? I'm not a pyro. At least not that you know. The thing about fires is there are some elements that burn very quickly and very hot. You throw dry leaves into a fire, they just, and it's awesome, and it's very fast. They don't have a lot of energy in them, which is why they burn quickly. And they burn brightly because they do have a lot of power. Energies are very powerful because the energy released from those leaves is very swift. A very large tree log, no matter how dry it is, has an enormous amount of energy, an incredible amount of energy. But because its volume is very large compared to its surface area, which is completely unlike a leaf, the amount of power you can draw out of a log is much harder. You don't get as much power as you would out of a pile of leaves. The same volume of leaves would have much higher burning power than the same volume of of a log. And the reason for that being, again, just that there's the surface area is much smaller. Leaves burn very quickly. They release energy very quickly because of the surface area they have. So when it comes down to it, energy and power are even related there when it comes to burning things in a fire. But being able to understand how energy and power are related is really important. For a lot of what we're going to be dealing with in this class, we're going to be talking about power more than we're going to be talking about energy. Now the reason for that is because energy is it's like a snapshot in time. How much energy do you have at 1 second? How much energy do you have at 3 seconds, 5 seconds? You have to look at it at a very specific amount of time. With power, you could be looking at how much power is being consumed at every second. Okay? How much power is being consumed? I mean, you can look at it at a snapshot. How much power is being consumed at this? What is the rate of energy release? For electrical circuits, because P equals VI, this equation is much easier. The equation for energy is not nearly as nice because it's the integral of power dt, and because power is equal to voltage times current, this is equal to the integral of VI dt. Now, I love calculus as much as the next guy, but it's not nearly as much fun in that respect. You have to come up with two different time-varying equations, multiply them by each other, figure out what the integral is. It's not my definition of a fun way to spend a good afternoon. There's not a lot of knee slapping. Calculating energy. Oh, it's integrating the voltage multiplied by current. So, woo! Now this plays a fundamental role when we talk about capacitors, which we'll get into later this semester. Again, I'm throwing words at you. But energy itself is much easier to calculate in a class like dynamics. Much easier to calculate in a class like chemistry. It's not nearly as easy to calculate power in those classes because it does require a derivative. So in this course we focus more on power. In those courses we did focus more on energy. And in a lot of Physics 1 we talked a lot about energy. Again, the reason for that is just because it's a lot easier to calculate kinetic energy. It's 1/2 mv squared. Okay, what is kinetic power? Well, how is that energy changing per time? It's the derivative of 1/2 mv squared. Which is awesome. Okay, so for this class, power is much more convenient. We will be focusing on power. But do realize that the power is related to the energy. Energy in this class is going to be used extensively with capacitors. I may ask you how much energy has been expended to heat through a resistor. You're going to need to know, okay, how much power is being, well, multiply V times I, and then take the integral with how much time. If the voltage and the current is constant, well, then the integral here becomes VI delta T. Okay, if V and I are constant. So that's, there are some conditions to this by which we can make our math a little bit easier. If V and I are not constant with time, then the energy becomes a lot harder. All right, so power and energy, foundational to this course. Now I am not going to teach for 2.5 hours today. Again, I don't hate you. I really don't. And let's not do that. But what I will do for today is I'm going to finish out this class by talking about some of the other important components that we're going to be talking about in this course. Okay, so in recap, voltage is the amount of energy per the electrons. Okay? Current is the amount of electrons traveling per unit of time. Power, in an electrical sense, well, in a general sense, it is energy consumed per time. In an electrical sense, this is equal to the amount of voltage multiplied by the current, which is the energy per electrons multiplied by the number of electrons per time. Okay. Energy, well, it is just energy. It's the ability to do work, which you could say it's the integral of power dt, which is equal to the integral of voltage times current. dt. Okay, so those are the basic terms. You absolutely need to know these. If you don't know these, you'll be lost in this course starting next class. I've tried to do my very best to beat the tar out of this topic. If you don't understand what any of these 4 terms mean, please send me an email. Let's have a Zoom meeting, sit down, let's hold hands, sing Kumbaya. Virtually, of course, because if I touch you, apparently I have to be afraid of all of you because Rona. I'm not afraid of you. I'm only afraid of your diseases. Okay, just if you don't understand these, please reach out to me. Please talk to me. I will help you as best as I can. I don't want you to fall behind on the first day of class. This is hard stuff. Okay, but now I'm going to bring in a couple of other terms. Okay, resistance. Resistance is the difficulty for an electron to move. Okay. If we're going to go back to our analogy of water, if I have a water pipe, okay, and I have a bunch of water, it's just traveling through, I can figure out how many gallons of water are passing through this pipe per second, which is the current. It's very, very analogous there. I have some current of water flowing through. Now, at some point, I'm going to have a giant valve that restricts the amount of water. It's going to prevent the water from just freely flowing through that pipe. Okay, a little bit of water that flows through really nicely, and most of the water will not. Okay, this valve makes it harder for water to flow, which reduces the current or requires more energy to push that water through that very small hole. Okay, so resistance, this is the reason why Ohm's law is true, is because here voltage and current are linearly related. You either need more energy to shove all this water through that hole, which means more pressure in the water. It can travel at the same speed with higher pressure, or you need more water flow. Make the pipe bigger to get through that. Okay? In either case, it's going to increase the energy. So, resistance is the difficulty for an electron to move. That is the foundational understanding of it. Okay? Now, this difficulty for an electron to move does create heat. We are going to adjust this definition, later on in this class as we get closer to RLC circuits, because a resistance element this doesn't perfectly describe a resistance element. We'll talk about that later. But for right now in this class, think about how hard it is for an electron to move. That is resistance. Okay? This is also called impedance, because it is impeding the ability for an electron to move. You can think of a doorway like a resistor. Okay, if you have a whole gaggle of students wandering down a hallway going to class, a doorway makes it hard for the students to get through. You're not going to have a gaggle of students walking through a doorway all at one time. I mean, you can try. Everybody's going to get Rona, but it's not easy. It forces all the students to slow down and file in single order. Okay? Resistance is the difficulty for things to move. You put up a bunch of obstacles in a hallway that suddenly you have to navigate around. It's going to take you longer to get down the hallway. You have impedance. Okay? So that's what resistance is. Okay? Now, we're also going to be talking about two other terms, and these are a little bit more high level. Resistance is fairly easy to understand. We're also going to be talking about capacitance. Okay? Capacitance is the energy that is being stored electrically. Okay? If you have two electrical plates next to each other, there's going to be an electric field. That electric field requires energy and exists in the presence of energy. The whole reason why an electric field ever exists is because there's an energy value there. So because there is an electric field present, there is capacitance. There always is going to be capacitance anytime you see an electric field. Okay? Similarly, inductance is energy stored magnetically. The motion of an electron creates a magnetic field around it. That's something that you probably learned in physics too, at least. Joel teaches you that. I believe Joel taught you physics too. Energy stored magnetically is caused by electrons moving. Current is electrons moving per time. So having any amount of current is going to create some inductance. Okay? We can ignore that inductance value. There are some variables that are associated with it by which inductance cancels out. Most of the time, I will point out to you whether or not an inductance is present. But in pretty much every circuit, if there is a current, there's going to be some small amount of inductance. And there are some components, namely those things. I cannot remember the name right now. I am blanking. But they are specifically designed to take current and transform it into a very large amount of magnetic energy. Okay? So if our energy is heat, it usually ends up as resistance. If our energy is electric field, it usually ends up as capacitance. If our energy is magnetic, it usually ends up as inductance. Okay? And each of these three are going to have different relationships between voltage and current. I'm going to, in the next class, share what those relationships are. I'm going to give you every formula we are going to use in this class. I will give you all of them. Next class. Okay, not in the next video. We have to talk about Kirchhoff's laws first. But on Thursday, I'm going to give you every formula we're going to use in class. And I'm going to do it first week. Everything that we do is a derivation of understanding these terms as well as the two Kirchhoff's laws. I believe you covered some Kirchhoff's laws in physics too. I'm going to beat you to death with Kirchhoff's laws. Okay, that's a threat. You've been threatened with knowledge. Kirchhoff's laws are also foundational to this course. All of these terms are foundational. Kirchhoff's laws are the two that complete. They are they're the 9 rings of power. And the one ring that rules them all is Elon Musk. I will see you all on Thursday. Actually, I will not. I will see my camera on Thursday. We'll have a great conversation. I will yell very angrily at my camera, and I will picture all of your faces when I do so. So, have a good day. I'll be posting your quiz later today. That will be due next week. So, get to it. Good luck. Email me if you have questions. This week is weird with office hours. Just email me. I will try to get back to you immediately. We can set up a Zoom meeting personally if you need it. Don't be afraid to talk to me. I love talking. All right. But other than that, this is the last lecture for today, and I will see my camera on Thursday. You will see me on Thursday if you watch the video on the day it's posted. Otherwise, you won't see me on Thursday. But that's your choice.